Let us start then. Good evening to all. Welcome to the sixth week problem solving session of NPTEL course Principles of Hydraulic Machines and System Design. My name is Ananthakrishnan. I'm a Ph.D. student from IIT Delhi. I do this problem solving session as part of my PMRF TA duty. So the contents for this week will be degree of reactions in pump and radial pump testing. And we'll see a few multiple choice questions and a few numericals based on these last week's lectures. So we can move into the questions. So just look into the first question and try to solve it. Meanwhile, I'll also try to solve it after only. Are you able to solve the answer? Which out of these four options is the right option for this question? Degrees of reaction for a pump can be given by ideal dynamic pressure rise divided by ideal static pressure rise, or is it ideal total pressure rise divided by ideal static pressure rise, or is it 1 minus ideal dynamic pressure rise divided by ideal total pressure rise, or is it 1 minus ideal static pressure rise divided by ideal total pressure rise? Which one of the four, which out of these four options is the right answer? Uh, am I audible or is my screen visible?
Yes, the screen is visible, but the audio is actually shuttering sometime.
One second, let me change the audio mode once. Am I audible right now? Is it better compared to the previous case? Can you tell me whether I'm audible right now? Can you unmute and tell me? I'm not able to hear anything.
Sorry, it's okay. It's not that great, but actually we can uh, hear.
Am I audible right now? Am I audible?
Yes, sir. It's you're audible, but
Okay.
actually there is some shuttering on in between. That's sometimes.
Okay. Today I'm using headphones. Should be that's the reason. Okay, so the answer to this question is there is 1 minus ideal dynamic pressure rise divided by total pressure rise. So the degree of reaction of a pump is defined as the ideal static pressure rise divided by ideal total pressure rise. So the total pressure rise component is equal to the sum of the static pressure rise and the dynamic pressure rise. So substituting this in the degree of reaction equation, R is equal to, we'll get it to be the static pressure rise can be substituted as the total pressure rise minus dynamic pressure rise. We'll get it as total pressure rise. The ideal case minus ideal case of dynamic pressure rise divided by ideal total pressure rise. So it will come out to be 1 minus ideal dynamic pressure rise divided by ideal total pressure rise. So the answer is option 3. So this is the degree of reaction for a pump. That will be the total static pressure rise in the ideal case divided by the total ideal total pressure rise in the pressure. So the total pressure, it will be having two parts. One is the dynamic pressure and the other is the static pressure. So yes, now we can move to the next question. Just look into the problem. It's a problem related to degree of reaction itself. In the case of axial pump design, if degree of reaction is zero, then which out of the four options is right? Static pressure rise is zero, static pressure rise is maximum, total pressure rise is zero, both A and C.
Sir, option A.
Yeah, yes. So the degree of reaction itself, the statement says that it is a static pressure rise, uh, ideal static pressure rise divided by the ideal total pressure rise. If degree of reaction is zero, then the numerator is zero, that is the static pressure is zero. The option A is correct answer. That we can move to the next problem. So these are just continuation of the same concept on degree of reaction. So we can just move quickly through these problems so that we can attend the numerical problems towards the end. The contribution of static pressure rise and dynamic pressure rise will be equal for the axial pump when degree of reaction is zero, degree of reaction is infinity, degree of reaction is 0.5, and degree of reaction is 1.
Sir, 0.5.
Uh, when the degree of reaction is 0.5, the contribution of static pressure rise and dynamic pressure rise will be same. So that is based on the uh, concept of degree of reaction. The formula of degree of reaction itself is the static pressure rise divided by static pressure rise plus dynamic pressure rise. So before going to the answer is right, degree of reaction is 0.5. So we can, before going to the next problem, we will try to derive the final equation for the degree of reaction. So the degree of reaction basic equation states that it is 1 minus dynamic pressure rise, that is the static pressure rise divided by total pressure rise. So we can write as 1 minus dynamic pressure rise divided by total pressure rise. So this is the equation 1 minus dynamic pressure rise divided by total pressure rise. So in the case of a radial flow pump, how we can derive this equation, that is something which we are going to see right now. Consider this to be the hub of the impeller, and this is the blade. multiple number of blades are there. So this portion is zoom out and try to draw the velocity triangle at the inlet and the outlet. So in that particular case, this is the actual velocity at the inlet. We assume a swirl free flow in this particular case, and then this is U1. Since it is swirl free flow, alpha 1 is equal to 90 degree. U1, beta 1 is the blade angle, and this is the relative velocity at the inlet. At the outlet, we will try to draw a similar velocity triangle. This is relative velocity omega 2. The angle which the blade angle at the outlet, the blade angle it makes with that of the tangential velocity U2, and then the velocity C2. And this is a vertical component, that is flow velocity component of the actual velocity term. So at the inlet, since this is a swirl free flow, CR1 is equal to C1. We can write it like that. But since we assume that the flow velocity component remains a constant in between the inlet and the outlet, so we can assume CR1 equal to CR2 from this diagram, so that the flow velocity vertical component remains the same, assuming that there is no variation in the discharge. So if you assume that there is no variation in the discharge, we can assume an almost constant cross-sectional area, and thereby we can assume it to be both the flow velocity terms CR1 equal to CR2. And now we try to reduce this basic formula of the degree of reaction. So R is equal to 1 minus dynamic pressure rise divided by total pressure rise. So the total pressure rise term, if you assume swirl free flow, we can write to be U2 into C theta 2, U2 into C theta 2 divided by G, that is the total head term. So we write this in terms of head. So then the other question will be, what will be the dynamic pressure rise? So the dynamic pressure rise will be the change in kinetic energy between the outlet and the inlet. So that will be C2 squared minus C1 squared divided by 2G term. So this will be the dynamic pressure rise term. So we'll try to reduce it. So we'll get C2 squared minus C1 squared divided by 2 times U2 into C theta 2. In this analysis, we have written that CR1 equal to CR2, but since this is a swirl free flow, we can assume CR1 is equal to C1. So then the question will be how to change this numerator term to some quantity which we know. So in this particular analysis, C1 is equal to CR1 equal to CR2 we know. Therefore, we can write C1, we can substitute C1 as CR2 squared divided by 2U2 C theta 2. So we have got comparison between two quantities, two velocity terms at the outlet of the blade. That is, one is the actual velocity and the other one is the flow velocity term. So this particular term corresponds to the tangential component term, the square of the tangential component term. So it will come to be 1 minus of C theta 2 square, C theta 2 square divided by 2U2 C theta 2. It will come out to be C theta divided by 2U2, 1 minus C theta divided by 2U2. This is the intermediate step in which we can express the relative, the degree of reaction in terms of the tangential velocity at the outlet and the blade velocity at the outlet. Now we can further reduce it using the blade angles and other parameters. So from the velocity triangle at the exit, we can write C theta 2 as U2 minus W theta 2 divided by 2 U2. This particular quantity. Now what we can do is that we will subtract. We will divide the numerator by the denominator. Numerator will be having two parts. So both of them. So it will reduce to, that implies R is equal to 1 by 2 plus W theta 2 divided by 2 U2. So this particular quantity we can obtain from the, instead of this W theta 2, that is a tangential component of the relative velocity, we can try to express in terms of blade angle as well as the flow velocity term. So taking this triangle, tan beta 2 is equal to CR2 divided by W theta 2. So W theta 2 can be substituted as 1 by 2 plus CR2 divided by tan beta 2 and theta 2. So this is the final so we have reduced this equation from the original basic theory equations. This is the final equation of degree of reaction that takes into account the flow velocity term at the outlet, the blade velocity, and the blade angle term. So if the degree of reaction, in the case when the degree of reaction is equal to half, what particularly happens is that left hand side term and this term will cancel out and we'll get CR2 equal to 0. In that particular term, CR2 will be equal to 0 when the degree of reaction is equal to 0.5. CR2 is the flow velocity term at the outlet will be equal to 0. That means that the entire velocity will be having a swirl component. The actual velocity component will be equal to 0. The actual velocity's entire component will be taken up by the swirl component. The flow component will be equal to 0. We can move to the next problem if no questions are there.
So,
Yeah.
so,
Yeah.
but actually, when I first calculated this, I actually used the base equation to calculate it. So, is there any problem if we calculate it like that? I
No,
mean,
there is no problem. There is no problem. This is just for the elaborate understanding only. I have tried to solve this and try to arrive at this final equation. It is not at all required for solving this problem. For solving this problem, only the base equation is sufficient based on the theory.
okay, sir.
Look into this problem. It's a true or false question. Head developed by the axial pump in case of no swirl at the inlet is 0 when outlet blade angle and degree of reaction is 0 degree and 1 respectively. This is a statement true or false. When no swirl is at the inlet, outlet blade angle and degree of reaction uh, and such that the outlet blade angle and degree of reaction are 0 degree and 1 respectively, head developed will be 0. So that is the statement. Is it true or false?
False. Because the blade
Yes.
angle should be 90 degrees.
Yes, right. The answer is false. So the actual head, the ideal head developed by a pump is given by the formula u2 c theta 2, that is the blade velocity multiplied by the tangential velocity, u1 c theta 1 divided by g. So when there is no swirl, that is tangential component of the actual velocity at the inlet c theta 1 equal to 0, we can reduce it to be u2 c theta 2 divided by g. And based on the outlet velocity triangle that we have seen the previous diagram, c theta 2 can be represented in terms of u2 and the tangential component of the relative velocity term. So this it can be written as u2 into u2 minus w theta 2 divided by g. And now we also know that from the velocity triangle, CR2 divided by W theta 2 is equal to tan beta 2. This is flow velocity component divided by the tangential component of the relative velocity is equal to tan beta 2. So we can write the omega theta 2 in terms of a CR2 and we can substitute that particular value in this equation. We get it to be u2 into u2 minus CR2 divided by tan beta 2, the whole term divided by G. So we have got a reduced equation which considers the blade angle, the relative velocity, the flow velocity component of the axial velocity, and the blade velocity term. Now in this particular equation, we can try to reduce so this is the particular equation for head, reduced equation for head. And the specific case in this particular problem is that the degree of reaction equal to 1. So R is equal to 1. So that is a specific constraint given in this problem. And we need to check whether this is possible at a blade angle of 0 degree. So we know that in this particular problem, we have to substitute blade angle equal to 0 degree and the degree of reaction is equal to 1. So the degree of reaction is given by the formula half plus half into, we have seen in this previous question, it's half plus half into CR2 divided by tan beta to U2. CR2 divided by tan beta to U2. So when the degree of reaction is 1, so CR2 equal to tan beta to U2. So we can substitute that particular value of CR2 in this particular equation 1. We'll get H is equal to U2 divided by G into U2 minus, we substitute CR2 equal to tan beta 2 into U2. We'll get it to be U2 equal to 0. So we'll get head is equal to 0 when we'll get head is equal to 0 if and only if the particular term tan beta 2 will be when beta 2 is equal to 90 degree. When tan beta 2 value tends to 1 by tan beta 2 value tends to 0. So only at that particular angle we'll get the total head value equal to 0. In all other cases, it will not be 0. So we have to assume it like that and consider the blade angle is equal to 90 degree to get a degree of reaction equal to 1 and head is equal to 0. Outlet head, the head produced by the pump will be 0. This is possibly if and only if beta 2 is equal to 90 degree. If beta 2 is not equal to 90 degree, then this is not possible and degree of reaction will the head produced will not be equal to 0. Look into the problem.
Option B is correct. 1 and 2.
Check the question once again.
So incorrect. Option C is the correct one.
Yes, the answer to this problem is option C. The schematic of the entire pump line for piston. This is suction pressure gauge, and this is a delivery pressure gauge, and this is all. And this is the delivery side. Delivery side. This is the head, and this is the discharge head. The other one is the suction static head. This is the discharge head. Static side. This is the pump. The discharge control valve is fitted in the delivery pipe. That is a right statement. The suction pipe is provided with a foot valve and strainer. So this part will be having some kind of strainer and foot valve. So that is also right. The suction pipe has a smaller diameter as compared to the discharge. So this statement is wrong. To understand it, we have to derive the actual pressure at the inlet to the pump at the pump in impeller IE area. If the suction side pressure PS is given as the gauge pressure PS is given as negative of Vs squared. That is a suction velocity. The velocity in the suction pipe plus the static head or the height above the sump where the pump is installed and the friction head losses. So this total pressure PS, the gauge pressure, that is P minus P atmosphere minus P at the eye of the impeller is given as PS. So that is equal to negative Vs squared divided by 2G plus Hs plus Hf. So this particular term is identified from applying the steady flow energy equation between the inlet sum point as well as the inlet to the eye. So that will be given as if we compare between the point 1 here and the suction side as point, we can write it as this steady flow energy equation as P1 divided by rho g plus V1 square divided by 2G plus 2G plus equal to 0 equal to the pressure PS divided by rho g plus Vs square divided by 2G plus Hs plus HFS. P at the I point. This velocity will be same as a suction velocity. This V1 will be very much lower than that of the suction side velocity, as the area in this particular column will be very large compared to the area at the impeller of Y. So this is approximately equal to 0. We can write P1 minus Pi divided by rho g as suction pressure PS divided by specific gravity rho g, specific weight rho g equal to P actually the other way around. Pi Pi minus P1. P1 is P atmosphere. This particular term P1 is equal to P atmosphere. So Pi minus P1 divided by rho g is equal to PS divided by rho g. Is given as negative of Vs squared divided by 2G plus static head plus frictional head loss in the suction pipeline. And this particular term, this is the gauge pressure, the pressure which is less than the atmospheric pressure. If the pressure at the impeller eye is very much less than that of the vapor pressure of the liquid at that point, there is every possibility of a cavitation and corresponding static pressure. Pressure or the output of the pump will be compensated. The output of the pump will severely come down. The head produced by the pump will also come down if the cavitation is present. So to prevent that, this particular term, the whole negative term, the magnitude of this term should be very less in order to be somewhere near the atmospheric pressure. It will be definitely less than the atmospheric pressure, but even then it shouldn't be dropping that much. So the whole magnitude term should be very less. How to reduce magnitude? There are only three options. One is we can reduce this static head, but that is no problem, and that is not a possible thing for our already installed system. Otherwise, you have to go for the basic philosophical change, move to submersible pump or something. And the other one is reduce the velocity in the suction side, and that corresponding velocity will also reduce the friction head loss in the suction pipeline, as it is dependent on the velocity and the suction pipeline. So this suction velocity Vs is dependent upon the diameter of the suction pipeline. So if we can provide a larger diameter in the suction pipe, the velocity term can come down, and the whole gauge pressure term can also come down, reducing the possibility of the uh, cavitation. So the only option is velocity in the suction line to reduce, and correspondingly, the suction diameter of the suction pipeline should increase. So the only incorrect option among the three options given are suction pipeline has a smaller diameter compared to discharge pipeline. In most cases, it will be higher. In some cases, it will be almost same as that of the discharge pipeline because of this cavitation issue. Problems are there, we can move to the next question. Read through the problem.
Option 2.
Yes, right.
Thank you.
The answer is right. The reduction in the suction head that can be used, that can be an option to reduce the cavitation in radial flow pump. The explanation follows the previous question's explanation, where the suction head, the total suction head is given as the static head intersection. So this the gauge pressure is given as Ps divided by rho g is equal to minus of the static head, suction static head plus the friction head intersection side plus the velocity part. So if we can reduce the magnitude of this quantity, we can reduce this one, and such that the actual pressure P at the eye will be almost P at the eye will be sufficiently higher than the vapor pressure of the liquid at that particular temperature. It's the gauge pressure at the inlet. So that particular quantity is equal to minus of Hs plus Hff plus V square divided by 2g. So this whole term, this is a static part of the suction head, and this is the friction in friction part of the suction head, and this is the dynamic velocity part of the dynamic head of the suction head. So if we can reduce this whole quantity, the magnitude of this quantity, we can ensure that this whole quantity reduces, and this cavitation can be avoided as the pressure will be sufficiently higher than that of the cavitation, the vapor pressure of the liquid. So we can, if that is not an issue, you can move to the next problem, which is the following statements is true for the radial flow testing. Initially, the delivery valve remains fully closed. Priming operation is done. Non-return valve is used to ensure one-way flow. All of the above. So which of the following four options are right in the case of radial flow testing?
Option 4 is correct. All of the
Yes,
above.
right.
Thank you.
In the case of the radial flow testing, all the three steps are followed. First of all, delivery valve will be fully closed, and then priming operation is done to flush out any vapor which is present in the in between the impeller, and then a non-return valve is closed, uh, and this non-return valve is used to ensure that the flow once you close this, once the impeller stops, the fluid which is already uh, present in the delivery head will not retract, will not come back, and then force the impeller in the opposite direction. To prevent that, we are using a non-return valve. Uh, to prevent that, we are using a non-return valve at the exit of the pump in the delivery head, in the delivery pipe. And this will ensure that the pump health will be in good condition, and there will be longevity for it as well. So this non-return valve is a crucial aspect in the case of pump testing. And then there is priming operation, and this will be the sequence. Initially, the delivery valve will be closed, then priming will be done. Then once the pump is operational, then non-return valve comes into picture, which will allow flow only in one direction from the pump to the delivery side, not from delivery side to the pump side. And that's why all the options are right. This is a multiple choice question. Just look into this problem. This is a numerical problem that takes into upon the things which were taught in the previous week's lectures. So this is a simple problem. We can just try to solve it. But to consider the heads across different points in the line between the suction line as well as the delivery line. The centrifugal pump is running to deliver 0.048 meter cube per second of water to a height of 24 meter through a pipe 150 mm in diameter and 120 meter long. The overall efficiency of the pump is assumed to be 75%. Also note that head loss due to friction in the pipe is 11.89 meters. Find the power required to run the pump.
Option 4 is the correct answer.
Right, right.
So the question, in the question, we need to determine the power required to run the pump. So the overall efficiency term is given as 0.75. Overall efficiency is considered as the power input, the actual head developed by power input in terms of meter. So this particular term, actual head developed, is not the ideal head developed by the pump, but it's actually the manometric head. So this will be the manometric head divided by power divided by rho g. So this will be giving the overall efficiency, and from that we can calculate the power. So power is equal to rho g q h mano divided by overall efficiency. This manometric head H mano is a combination of the total static head, that is HS plus HD, that is the height from which the pump is going to pump water from sump level to the overhead tank. And the second factor in this one will be the frictional head losses related head. So in the suction side as well as in the delivery side, there will be friction related head. And the third parameter, this is a static head term, and this is the suction plus delivery friction losses, friction head. And the fourth term will be the velocity related dynamic head. So all these three terms will be included in the manometric head. So this static head will be 24 meters given in this problem. The frictional head losses, it's been mentioned that the head loss due to friction in the pipe is 11.89 meters. And then the dynamic pressure Vt squared divided by 2g can be derived from the discharge which is delivered by the pump. So this discharge which is delivered by the pump will be having is given as can calculate the velocity as the discharge divided by the diameter area of the pipe. So it is 2 divided by pi by 4 into d squared. So it will be 0.048 divided by pi by 4 into diameter is 150 mm. So it is 0.15 squared. So you'll get it around 2.7 meters per second. So we substitute that 2.7 squared divided by 2g. We will get the manometric head. The total manometric head, it will be coming around 36.26 meters. So the total overall efficiency is given as 0.75. Can calculate power as rho GQH mano divided by overall efficiency. So this density in this particular problem is 1000, 9.81, and manometric head is 36.26. Discharge is 0.048 divided by 0.75. So that will be coming around 22,760 watt. So in terms of kilowatt, it will be 22.76 kilowatt. So the answer to this problem is 22.76 kilowatt. So it takes into account all the heads which are included in this pipeline from the suction strainer to the delivery or delivered overhead tank. All the heads will be taken. One is the static head. That will be the height of the from the suction strainer to the overhead tank. What will be the basic static height? So that will be the static head term. And then there is a dynamic head that will take into account the velocity within the pipe. And then the third term is the suction friction head in the suction and delivery pipes. So all these three combined together to give the actual the manometric head. The manometric head will be related to the power input by using the overall efficiency, which is given in this problem. So using that, we can calculate the power available, power required by the pump to deliver water from this suction strainer to the overhead tank, covering this much head loss. So we'll get the power required in the pump as 22.76 kilowatt. Can go to the next problem. Just look into this problem. It's a two-part question. First part will be in the 9th, and second will be in the 10th. 10th problem. Just look in this problem and try to solve it. The question says a pump with an impeller having internal and external diameters 240 mm and 480 mm respectively runs at 100 rpm. Consider flow rate through the pump is 0.0576 meter cube per second. Take the constant velocity of flow equal to 2.4 meter per second. The diameters of the suction and delivery pipes are 180 mm and 120 mm respectively. In addition, suction and delivery heads are 6.2 meter and 30.2 meter of water respectively. The power required to drive the pump is 23.3 kilowatt and the outlet vane angle is 45 degree. The inlet vane angle will be which one of the following options? Is it 9.5, 11.3, 7.9, and 10.8? So in this particular problem, we do not require most of this information. This is a joint question between 9 and 10. That's why the same a lot of extra information is provided in this question. So in this particular problem, we need to calculate, we need to draw the velocity triangle in order to identify the required options required, the options which are required in this particular problem. Consider this to be the way. Consider it to be a swirl free flow at the inlet. So we take Vf1 is equal to V1. And this is the relative velocity, W. So see, it's C. So this is W1 and this is U1. This is the blade angle beta1 that we need to calculate the inlet vane angle at the outlet. This will be the relative velocity is W2. So U2 blade velocity, and then this is the actual velocity V2 term. This C2 alpha 2. This is beta 2. And this is CR2. In this particular problem, the so to see it, this is CR1. In this particular problem, we have been given CR1 is equal to CR2 is equal to 2.4 meter per second. We need to calculate the inlet vane angle. So we have to look into the inlet velocity triangle to get the answer, get the solution. So if you take tan beta 1 at for the inlet velocity triangle, it will be CR1 divided by U1. So this U1 CR1 is given as 2.4. If you calculate U1, we can get tan beta 1. U1 is a tangential blade velocity at the inlet. So U1 is given as pi into D1 into N divided by 60. So the inner diameter at the diameter at the impeller of the pipe for the centrifugal pump is 120 mm. So it will be that is the diameter. So it will be coming around. Diameter of the suction delivery side beg your pardon, that diameter is 240 mm. So it will be 240 at the inlet side to the pump multiplied by 100 RPM is given in the problem. So divided by 60.
So there is a error in the statement of the problem, I hope. A centrifugal pump cannot be running at a very low speed of 100 RPM. It should be 1000 RPM.
It's 1000 RPM. It's I beg your pardon, it's a mistake. It's 1000 RPM. Thanks. This is 1000 RPM. Just a mistake. It's 1000. And we'll be getting it around -3. Prices meter per second from the velocity triangle at the inlet. We get tan beta 1 is equal to CR1 is 2.4 divided by 12.56. So we'll get beta 1 equal to 10.8 degree. So the first part of the problem, we have to calculate the inlet vane angle based on the input parameters. So the second part of the problem, we need to calculate the overall efficiency of the pump. Overall efficiency, we need to calculate it's a relationship between the manometric head and the power input which is required in the pump. So we need to calculate that in the second part of the problem. The problem statement remains the same as at the first 9th question. So in this particular problem, we have got internal and external diameters of 240 and 480 mm for the pump impeller, and we also have a flow rate of 0.056 meter cube per second. The flow velocity is taken as 2.4 meter. It's a constant throughout the pump, throughout the impeller, and the diameter of the suction and delivery pipes are given as 180 mm and 120 mm respectively. This is useful, quite useful in order to calculate the suction and velocity, the heads associated with the suction and delivery pipes, and the velocities associated with it. The suction and delivery heads are 6.2 and 30.2 meters of water respectively. The power required to drive the pump is 23.3 kilowatt and the outlet vane angle is 45 degree. We need to calculate the overall efficiency in this case. In the second case, that is the 10th problem. a fairly straightforward problem. The second part of the problem, we really refer the efficiency, the overall efficiency of the system. The overall efficiency is given as the manometric head related power divided by the power input. In this particular problem, power input is given as it was mentioned in the previous problem statement. Power input is 23.3 kilowatt. So this term is 23.3 kilowatt. This is 1000 and 9.81, and the volume flow rate is given as 0.056576 meter cube per second. So that will be 0.0576 meter cube per second. And the overall efficiency we need to calculate. We do not know the manometric efficiency. We need to find the value of manometric efficiency and substitute in this equation to calculate the overall efficiency. So in the previous problem, in the question number 8, we have determined the manometric efficiency in terms of the suction heads and the delivery heads, which doesn't take into account the pump impeller side. The overall head, which is required to overcome the static lift as well as the dynamic lift and the frictional head losses will be equal to manometric head if you are considering the suction pipe and the delivery pipe. But in this particular problem, we are being given the suction, the suction and delivery heads are given as 6.2 and 30.2 meter of water. So this is considered at the pump datum line at the inlet to the pump and at the exit of the pump. So we have both this these heads 6.2 and 30.2, and we also need to calculate the this is purely pressure suction and delivery heads. This corresponds to the pressure head terms. Similarly, we will be having the velocity heads as well. That is equal to, that can be calculated from the volume flow rate, which is given, and the diameter of the suction and delivery pipes, and also the height at which the inlet of the impeller as well as the exit of the impeller are located. Normally, this will be considered, this will be neglected. The difference in height between the inlet and the exit are being neglected. So in this particular problem, in the next problem, if you calculate the manometric head based on the pump impeller inlet and the exit, so this is the inlet point of the pump. This is the exit point of the pump. This is B and this is X. So the manometric head is defined as the difference in head that is imparted to the fluid in the pump impeller by the external energy providing source. So it is the total head at the point D minus total head at the point S. So this total head at the point D is the static head PD divided by rho G plus VD squared divided by 2G plus Z at point D minus at the impeller inlet, it is PS divided by rho G plus V suction pipe square divided by 2G and Z. So if you neglect the difference in height between the discharge and the suction pipeline at the inlet and exit of the pump, you can neglect these two, and then it will come out to be this discharge suction head in the discharge head, the delivery head is given as 30.2, and the suction head is given as 6.2. That is the pressure head terms. So in this, it will be 30.2 and 6.2. So in this, the suction head in the is given as 6.2. We need to calculate the velocities at the delivery in the delivery pipe as well as the suction pipe. So VD, we know the discharge, can be written as Q divided by pi by 4 into d squared of the delivery tube. So the discharge is 0.0576 divided by pi by 4 into diameter squared. So that is diameter of the delivery pipe. So that is given as 120 meters. In the previous analysis, we have seen suction diameter will be higher than that of the delivery pipe diameter to avoid cavitation. The delivery side, it will be 120 mm. It is 0.12 squared. And similarly, for the suction side, it will be Vs is equal to Q divided by pi by 4 into diameter suction is equal to 0.0576 divided by pi by 4 into the velocity term will be 0.18 squared. In the delivery side, the velocity will be coming around 5.01 meter per second. And on the suction side, the velocity will be coming around 2.23 meter per second. So substituting these values of the velocity in this equation, Vd squared divided by 2g will be coming around 5.01 squared divided by 2g, and Vs squared will be coming around 2.23 squared divided by 2g. So overall, it will be coming, the manometric head will be coming as 25.03 meters. And substituting this value in the overall efficiency equation, so we'll get it a overall efficiency theta overall is equal to 0.023 to 25.03. That is coming around 59.7%. So the answer to this problem is option B. I hope the discussion related to this problem is understandable for you. If any doubts are there, you can ask the questions.
Sir, one question.
Yeah.
So PS by rho G, we put it as minus of HS plus HSF plus VS square by 2G.
Yes, yes.
But here, so minus of minus, it became plus, but here it is why we are subtracting.
No, actually, this is so absolute pressure. In the previous analysis, we have taken it as a gauge pressure.
Okay, okay.
No, you are asking about this problem, right? This this one, right? This is a gauge pressure term. Yeah, we are taking impeller eye pressure minus the atmospheric pressure. That will be the suction gauge pressure.
Okay.
Here it is absolute pressure in the last problem.
Okay.
No more questions are there. We can meet next week with the pump characteristics and system design lectures, and we can solve a few problems related to that.
Okay. Thank you. Thank you.
Thanks.